We're happy to have Christopher from Lockheed Martin on the phone, and I'm going to put him in the spot because I read his papers about space stations, and he's working on advanced technology issues that many of us only used to dream about when I taught in engineering schools. Right? So, Christopher, when you're thinking about autonomous vehicles up in space, in planets, and when you're thinking about Lockheed Martin's, not only its existing satellites, you guys know a lot about batteries. What do you guys see as the constraints in this deployment of batteries? Not just on what Tim's talking about, but from the point of view of the near future. Is there enough critical materials to create the batteries of the future? Christopher?
Hey, Bruce. Leo McKay's on too, so he may be able to jump in and help me out as well. But you may have seen, we actually recently put an announcement out that we're partnering, Lockheed Martin is partnering with GM to make the next lunar vehicle, and of course that'll be electric. People will be, you can go look at some pictures of it in theory, but there'll be a real one here before long. Flow batteries were mentioned as something that still had some problems, but actually Lockheed Martin is in the business of the GridStar flow battery, where we have some beta versions that are actually in production. Because as was mentioned, the materials and the cost of the lithium batteries, when there's so much need, both if you use them in the grid, if you use them in vehicles, it really starts to stretch the material supply. So the costs may become such that that other batteries, like flow batteries, might make more sense in some very large areas.
Leo, do you want to weigh in as the EVP at Lockheed? Thank you both for being here.
No, Christopher's closer to the base technology, and he's got a deeper engineering education. I also, in addition to my work at Lockheed, I also sit on the board of an energy utility in the Midwest, Ameren, and we worry about a lot of the things that were talked about earlier in terms of some of the second order challenges of going to of electrification, both with respect to the transportation sector, but also electrical generation and grid stability. Another thing that's not realized as widely as probably by this crowd, but maybe not as widely it should be, is that when you get a grid that gets to about 30% renewables because of the intermittent nature and because you may have mismatches between where power is generated and where electricity needs to be consumed, the management of the grid becomes a significant challenge, and the sophistication of the grid management and network management tools has to ramp up to meet that. One of the things that I'm somewhat concerned about is sort of simple-minded pushes to net zero 2050, and then it's all home free. I think this group understands. I don't think they're probably not insurmountable, but there are significant second-order challenges and prioritizations. That industry and then some society through its political organisms needs to make some decisions and priorities about it. And this is a great discussion with respect to that, and I appreciate that.
Thank you for your investment of time.
All right. Thank you for those perspectives. It's really helpful. So as electric vehicle sales ramp up, challenges loom large for lithium, cobalt, and nickel supply in particular. Lithium faces the steepest increase in demand, six-fold from the battery sector by 2030. Mined and recycled cobalt can only meet half of the forecasted demand by the middle of this decade. And the world will become even more dependent on the Democratic Republic of the Congo, and I'll talk about that more in just a second. Nickel will slip into deficit later this decade, and there's really no shortage in the nickel resource, but new mines are not opening because of significant ESG challenges. And if other battery chemistries experience some breakthroughs like lithium iron phosphate or lithium sulfur, lithium air batteries, the demand for cobalt and nickel would be substantially smaller. But I mean, we keep hearing about all the work that's being done there, but they just don't come to fruition. And I don't know. I guess we'll see. If this meme offends anybody, I apologize, but I wanted it to have an edge to it because UNICEF estimates that there are 40,000 child laborers, and they use the term loosely. Some people call them artisan miners, that are engaged in cobalt production in the DRC. And so if there are 40,000 child laborers now, how many are we going to need in 5 years, 10 years to mine the cobalt? I mean, something clearly needs to be done here. And it's just unfathomable to me in today's focus on equality and civil rights that this just goes on and on and on. But it does. So other supply chain challenges need to be considered for battery production is that 65% of battery production currently comes from China. To put that in perspective, no single country produces more than 20% of global crude oil output. You know, we often think of oil production being done by cartels and being tightly controlled. Well, that potentially exists here as well. China controls 80% of the world raw material refining, 77% of cell capacity, and 60% of component manufacturing for lithium-ion batteries. Japan and Korea rank number 2 and 3 respectively, but way down the list there. And very, very few of these batteries are currently recycled. They're not built for recycling. And the valuable materials, really the cobalt, nickel, and the copper, are in the individual battery cells. And these battery packs are comprised of hundreds of these cells. Those cells are built to withstand many years of use, not to be deconstructed, to get at the valuable components. And current recycling methods are very crude. You bust open the outer cell, the outer casing of the cell, the modules are shredded, placed in an oven. The lighter components like lithium and manganese burn. They leave behind an alloy slurry of the high value metals, and then those have to be treated with strong acids to recover and separated to recover the metals. And these processes require a large amount of energy, large amount of chemicals like acids, and consequently, and you end up with a lot of hazardous waste for disposal. So with that in mind, we'll switch gears and talk to hydrogen. So it's rapidly becoming a promising energy storage option for applications, obviously in grid storage, for transportation applications, especially large-scale ones. And I've got a graphic that kind of shows that here in a second. It's being used for heating applications now. It can be used for heating industrial processes. It can be used for heating office space, homes, and so forth. Some companies are blending hydrogen with their natural gas now, renewable hydrogen, to lower the carbon footprint of their natural gas. It's used in chemical production, particularly for anhydrous ammonia fertilizer. And recently have our project pending with ArcelorMittal to look at hydrogen for steel production as a substitute for coke or coal in the steel production process. So we could be producing steel with no CO2 emissions. So lots going on there. Usually when we talk about hydrogen, they frequently refer to it as colors that are based on the production method used to produce the hydrogen. Gray hydrogen is used to refer to hydrogen that is produced by using fossil fuels in a steam reforming process. Use steam to bust apart the methane to recover the hydrogen. The problem with that is it does give off CO2 emissions. 95% of hydrogen today is produced in this manner because it's the cheapest way to do it. It can be produced between $1 and $3 and change per kilogram. And when I talk about hydrogen, a kilogram of hydrogen, that's a significant measurement because a kilogram of hydrogen contains about the same amount of energy as a gallon of gasoline. So gray hydrogen is $1 to $3 something per kilogram. You can compare that to the price of gasoline. Blue hydrogen is produced with low CO2 emissions. So this would include hydrogen produced using nuclear power through a process called electrolysis. So you can split apart water. You can split hydrogen and oxygen from water with electricity. And so if you do that, and you use nuclear power, you have very little CO2 emissions. It can also be done with the steam reforming process using fossil fuels as a feedstock. If we sequester the carbon using some of the carbon capture and storage methods described earlier. And then green hydrogen is receiving a lot of focus now because here we're using electrolysis or electricity to split water using renewable power. And so the electrolysis, if the power comes from renewable assets, then the carbon footprint of the hydrogen that's produced is essentially nothing. It can also apply to the steam reforming process if you use renewable natural gas, say gas from anaerobic digestion of waste and that kind of thing. Green hydrogen currently costs $3, $4, something like that per kilogram to produce, but projections are that it'll go a lot lower, and I'll talk about that more in just a minute. But any way you produce it, whether you burn it directly in an engine or pass it through a hydrogen fuel cell device, which combines hydrogen with oxygen in the atmosphere to produce electricity, so you can drive an electric motor with it. Either way, your only emission in the consumption of hydrogen is water vapor. So there would be no CO2 emissions on the use side. The production of hydrogen from nuclear power is getting a lot of attention these days. Exelon, First Energy, Xcel, Arizona Public Service have all committed to pilot scale projects. There are two pathways to do this that are interesting. One is, again, just split it with the electricity you produce. The other is thermal decomposition of methane. That one's interesting because you can introduce methane into the process and essentially pyrolyze the carbon. So you end up with essentially carbon black, which is extremely valuable. So you'd have no CO2 emissions. You would produce carbon black, which is used in making all rubber products, right? So tires, conveyor belts. It's also used in the production of carbon fiber. So that is a really interesting.
Does that explain why Arizona Public Service, which owns the largest reactor, Palo Alto, and Exelon, which when we used to work for them, they own at least a dozen nuclear complexes. Are they interested in this pathway because they see an additional revenue stream to owning reactors?
Oh, absolutely. So nuclear power plants have off-peak times too, where they have extra power available, like in the middle of the night, that they can't sell, but they have to keep their reactors running. They could be using that capacity to produce hydrogen.
Interesting.
Right.
I never even thought of that, Tim. Interesting.
Yeah. So that is a big one. And so this chart shows, potential application. A lot of people, there's a lot of debate on, which is better, batteries or hydrogen. They're both here to stay. And how the market totally shakes out, I don't know. But based on the research I've done, it looks to me, if you look at travel distance versus vehicle size, for shorter distances and smaller vehicles, I think battery electric vehicles make a lot of sense. For large vehicles like locomotives and ships and airplanes, mining trucks, semi-trucks that travel long distances, I think the hydrogen fuel cell technology probably will make more sense. There will, of course, be exceptions to all this. And then there's some gray area in between here with buses, forklifts, delivery vans, that kind of thing. That could go one way or the other, again, depending on fleet size, depending on the distances traveled, your payloads, and all that kind of thing. But I think in general, these are the trends that are emerging.